Hello everyone. In this video, we'll take a look at the connectedness or connectivity in a graph. Take a look at this graph. In this graph, the nodes represent the cities and the edges represent roads. Now, if I go from one node to another, I take a road in between those two cities. So if I want to go from a particular city to another city, will it be possible for me to reach there? So this is what we try to address in the connectivity or connectedness. There are different basic terminologies that we have to cover. So first is the walk. A walk in a graph G is a sequence of one or more nodes such that any two consecutive nodes in the sequence are adjacent. That is, V1 and V2 should be adjacent, V2 and V3 should be adjacent, and so on. The length of the walk V1 up to Vn is n minus 1. Because there are n nodes in the walk, there will be n minus 1 edges, and hence the length is n minus 1. A trivial walk is the one in which the length is 0, that is, there is only one node. A trail in a graph is a walk that does not repeat any edges. And a path in a graph is the walk that does not repeat any nodes. So if it does not repeat any nodes, automatically it does not repeat any edges as well. All paths are trails, therefore. Okay, now we'll see some examples. Now this is an example of a walk, path as well as a trail. So let's say you want to go from San Francisco to Seattle. Okay. So you go from San Francisco to Sacramento to Portland and to Seattle. As you can see, no nodes are repeated and no edges are repeated. So it's a walk, trail as well as a path. Now there is another way to go from San Francisco to Seattle. Okay. You go from San Francisco to Sacramento, then to Salt Lake City, to Portland, and then to Seattle. It's a walk because all the nodes in this sequence are adjacent to each other. It's a trail because edges are not getting repeated, and it's a path because no nodes are getting repeated. Now this is an example of a walk because all the nodes in this are adjacent. San Francisco to Sacramento to LA to Phoenix to Flagstaff to Barstow. If I stop here, then it would have been a path as well. But now I have repeated a node and I went back to LA. So LA is repeated. That's why it is no longer a path. Okay. But it's a walk because all the nodes in the sequence are adjacent, and it's a trail because no edges are getting repeated. Now, closed walk, circuit, and cycle. So a closed walk in a graph is a walk from its node back to itself. A circuit is a closed walk that does not contain a repeated edge. And a cycle, also called as a simple circuit, is a closed walk that does not have any repeated edge or repeated vertex except the first and the last vertex. The number of vertices on a cycle is the same as the number of edges. Okay, because the first and last vertex is the same. Okay, so number of vertices becomes equal to number of edges. Okay, so the concepts that we saw just now are all related. The six definitions that we saw, basically walks, paths, trails, and closed walks, cycles, circuits, all these are related to each other. And now let's take a look at it like a Venn diagram. So basically, walks are of two types, open walks and closed walks. We call open walks just walks, okay, and closed walks. Now, when is it open? When start vertex and end vertex are different. And it is closed if they start and end at the same vertex. Now, inside that, the subset is trail or a circuit. Now, it is a trail or a circuit if there are no repeated edges. If there are no repeated edges in a walk and it is open, it's a trail. If there are no repeated edges in a walk and it is closed, then it is a circuit. Now, if we take a further subset of it with one more restriction added, that there should be no repeated vertices. So if a walk has no repeated vertices and it is open, it's a path. And if a walk has no repeated vertices and it is closed, then it is a cycle. Now, example of a cycle or a simple circuit. So let's say we want to start and end. So we want to start and reach Seattle back again. So from Seattle, we go to Butte City to Salt Lake City to Portland, back to Seattle. So this is an example of a cycle because start and end vertex are the same and vertices, any other vertices are not repeated. So it's a cycle. Now minimum length of a cycle has to be 3. Let's say we have a graph with one vertex and can we form a cycle of length 0? Now to form a cycle we'll have to have a edge, but this is not possible. We cannot have a self loop. Okay, so the number of vertices is not equal to number of edges. And another thing is there is a definition of forests. A forest is a graph without cycles, and a forest can contain isolated vertices like this. So in that case, if we define an isolated vertex to be a cycle of length 0, then the definition of forest gets violated. So it is not possible. Now what if we have a cycle of length 1? We cannot go to second vertex and return to the first vertex while traversing just one edge because there is no second vertex. Okay, so it is not possible. Now, what if we have two vertices? Can we have a cycle of length 2? Now, we are talking of simple graph, and simple graph cannot have multiple edges or loops. So there is one edge. Okay, we cannot go to second vertex and return to the first vertex without repeating the edge. Okay, so it cannot be a cycle of length 2. So now we are kind of summarizing what we studied. We are interested in walks or sequences of adjacent vertices which do not have a repeated edge, which do not have a repeated vertex, those that start and end at the same vertex, right? So this table summarizes all the terminology, okay, which we have already seen as a set theoretic concept as well. Now let's go to reachability and connectedness. A node V is reachable from a node U if there is a path from U to V. A graph G is called connected if all pairs of distinct nodes in G, all pairs, are reachable. A connected component or CC of a graph G is a set consisting of a node and every node reachable from it. So, if a graph is connected, that means you can start at any node and reach every other node. That is what we saw here. If it is not possible, there will be more than one connected components. So, if a graph G is equal to V comma E, has two or more connected components, then it is not a connected graph. We'll see the examples. Now let's say there is some work going on between Sacramento and LA and Las Vegas and Barstow City, and due to this there is road closure. Now, because of road closure, effectively, if you want to go from San Francisco to Seattle, you can still go using multiple paths. But if you want to go from San Francisco to Barstow, you see there are no paths available. There is no walk, there is no connection available. So effectively, we have two connected components within our graph, as you can see in these two rectangles. If you start from San Francisco or Sacramento, so if you start from any node within this upper rectangle, you can reach any other node. And if you start from any city within the lower rectangle, you can reach any other city within that rectangle. Okay, so these are two connected components. That's it for this video. Thanks for watching.